Okay, today we're going to go back and do some application of the last unit we studied on math modeling. Today you'll need your graphing calculator, and we're going to be looking at some examples in the book. So if you have your book, you can follow along with me. We are starting on page 454, and we're looking at curve fitting with some of our polynomial models. What they've given us in this example is a table showing the closing value of the stock index on the first day of trading for different years, and we have some from 1994 up to 2004. And we're supposed to create a mathematical model for this data to determine what type of function is most appropriate. And we're going to use what we've learned so far on how to determine what type of graph this is. Since we will be using our graphing calculators, make sure you have those out, make sure you have those on, but we're going to look at it algebraically first. Hopefully you remember we can look at our differences to tell what type of data we have. If our first difference is constant, then it is a linear function. If our second difference is constant, it's quadratic. If the third difference is constant, it's a cubic function. If the fourth difference, quartic, and fifth, quintic. So here's an example on that same page, 454 in your textbook. And if we look at table A, if we look at the y values, here's the first differences. -4 minus -10, 6. -1.4 minus -4, 2.6. So if we look at all of these are not constant in any way. So if we take the second difference, 2.6 minus 6, 1.4 minus 2.6. Here's our second differences. We look at those. Those are not constant. But if we take that third difference, -1.2 minus -3.4, 1 minus 1.2. If we look at that third difference, it is constant. So when our third difference is constant, that would tell us that this is best represented, this table represents a cubic polynomial. So once we've decided it's a cubic, then we can use our calculator to actually find the model, and we'll go through that process in a little bit. Let's take a look at another one. Here we're over on page 455. If we look at the finite differences, if we look at our y's, the first difference is not constant, the second not constant, the third not constant, but the fourth difference is constant here on page 455. So this would be best described as a quartic polynomial. Let's take a look at this. Check it out. We'll use that as you try. So take a look at this table. See if you can find the differences and determine the type of polynomial. If you'll hit pause on the video, and when the students are ready, press play, I'll have the answer ready for them. Okay, back with you now. And did you find that this was best represented by a cubic polynomial? So if we looked at this data, the third differences should have been constant. Okay, let's look down at the next example. Now, that is not your bell. Please ignore that bell. If we look at this table of data and we look at the first differences, not even close. Second differences, not close. But the third differences are close. They're not exact, but they're close. So that would tell us that this is probably close to a cubic polynomial. So what we're going to do is we're going to enter our data on the calculator and do a cubic regression for this data. And we're going to practice that in a minute, but right now let's just take a look at this screen. So when we do a cubic regression, do you see it shows a cubic polynomial because our leading term is the third degree. And then it tells us what these coefficients for A, B, C, and our constant D are so that we can model this equation. So if we were to write an equation that modeled this data, it would be y equals, I'm going to do a little bit of rounding here. I'm going to say 1.21 x cubed plus, actually the next one negative, so minus 4.211 x squared plus, and I'm going to carry it down to the next row, 146.365x plus 2,851.643. Now, this does model the data we're given here, and then we can use this to make predictions. If we've noticed a trend, which we do, we could predict the population in 2010. Well, we're already past 2010, so at this point we could go back and actually compare that to what the prediction would have been. And we can use it to predict 2020 if this trend continues. So this is helpful to be able to model data, to make predictions about things that would happen in the future. That way you can prepare for growth in infrastructure. Okay, let's take a look at the next one. All right, on page 456, here we have a finance application, and this gives us, this is the data from the stock index. So the first thing I'd like you to do is take a look at this, and I would like us to put this data into our calculators. So let's all turn our calculator on, and the first thing I want you to do when you have your calculator on is we need to turn the diagnostics on. So let me show you where you can find the diagnostics. If we do second and 0, second and 0 takes us to catalog. And then if we go down to D for where we can find diagnostic, whoops, well, that didn't work on mine. Okay, I'll just arrow down until we get to D. It might work on yours, it should. And we will turn the diagnostic, there it goes, a little too far, turn our diagnostics on, because this is going to give us some statistical information that we need to create these models. So turn your diagnostics on. Hopefully you got there a little quicker than I, and just, I had absolute value bars. I have no idea where the absolute value bars came from. Well, we will try this once again. Clear. Okay, second catalog and arrow down to diagnostic. Works a lot better on a real calculator instead of my computer simulated one. There we go. Yay, mine are finally on once I hit enter. And so you should see diagnostic on and done. Okay, now we're going to go in and enter that data, and hopefully you remember how to enter the data. Go into statistics, go into edit, and we're going to enter our data. So let's take a look at our data, and our data is this data right here. Now I'm going to let this be year 0, so this would be 1, 2, 3, and then 2000 is how many years after. So 98 would be 4, 99 would be 5, so this would be 6, 7, 8, no, skipped 8, 9, and 10. Okay, so that's what we're going to do. We're going to enter this for our X values, this for our Y values, and let's do that together now. So we're going to enter our data. And I can't see the other data, so we will do this together. 0, and then 1, 2, 3, and then we skipped 4 and 5. We went to 6, 7, skipped 8, did 9, and 10. Okay, and for our Y's, we have 774, 751, 1053, 1293, 4186, 1347, and 2011. Okay, so first thing we're going to do is we're going to graph this data. So if we hit second and Y equals, we're going to turn our stat plots on. So we'll go up to, if you have extra turned on, turn one of them off, but we're going to go into 1. I'm going to turn it on, so I'm going to highlight the on. I want a scatter plot, so there's a scatter plot. I put my data in L1 and L2. Now if yours is not showing L1 and L2, just hit second 1 for L1 and second 2 for L2. So go ahead and make sure you have that set up. And then once you have everything, you can quit out of that. Second mode quits out of that. And then what we're going to do is we're going to do a zoom stat. So hit the zoom button and we're entered our data into the statistical model. So we're going to zoom stat, which is choice 9. Zoom 9. Well, let me go back and look at I have an error. Stat, edit. Did I enter an extra number? L1, L2. I did not enter enough numbers over here. $7.74, $7.51, $10.53, $12. Okay, my first 4 numbers match. That's where I missed one. 24.74. 13.47. Well, good. This way you get to see everything that you should do if you get an error message. So if it says dimension mismatch, then you failed to put the equal amount of data into each column. So hopefully you didn't, but let's try it again. Now we should be able to zoom 9, and there's our data. So what do we think this looks like? What kind of model could we choose for this data? So looking at our data, we have to start making some choices. I see maybe a curve to it. So I'm thinking maybe a cubic, because we can think about the number of maxes and mins. Possibly a quartic. We could look at those third and fourth differences. And there's also something else we have at our disposal. So let's take a look at, let's go back into statistics. And we're going to calculate a cubic regression because we see that max here, the min here, maybe it could be a cubic. And then we're going to look at a quartic too, just to compare the two. So if we come down to cubic, because we think it looks like it has the max and the min, and we go into cubic, it asks us where we put them. I put them in L1 and L2, and we're going to calculate. Okay, now what we're going to talk about now is this last number, the square of the correlation coefficient, R squared. The closer this number is to 1, the closer R squared is to 1, the better the fit of the data. So if we look at this, our R squared for this one is 6.27. Whoops, and I'm trying. Let's see if I can highlight it. There we go. So now let's go back in, and with the same data, let's do a quartic model. So we're going to do second stat. Not second, excuse me, should not have hit second, just statistics. And then now we're going to calculate a quartic, which is choice 7. My data is still in L1 and L2, and I'm going to calculate that. Now, it gives us all the coefficients we need, and let's see what R squared is. So in this case, our R squared is 0.84. So of these two models, the quartic is the better fit because our R squared is closer to 1. Now, if we wanted a great fit, we'd really want an R-squared that was like 0.95. So this is a better model for the data. It may not be the best. It is a better model for the data than than a cubic. So in this case, I would go with a quartic. I would pick off all these coefficients, plug it in, and you have an equation that models this data. So what would that look like? It would look like this. The function is equal to, let's come back up here and take a look at our A. I can arrow back up to find the A. The A is the 0.926. So we would say, and it would round to 9.27, x to the fourth minus 191.56, x cubed plus 1168.22, x squared, and we are just taking the coefficients that they're giving us here and plugging them into the model. And then that would be 999.60. So we can use that model to make predictions. What do we think this starting would be in 10 years from now? Okay. Now, the next section, this is 15.2. Other functions that we looked at other than polynomials, we looked at exponentials. So instead of there being constant differences like there were with linear, with exponentials, we were multiplying by the same number over and over again. We're looking at the common ratio. So on 461, it shows us this one is linear because the first difference is constant, but this one is exponential because the ratio times 2 times 2 times 2 times 2. My first differences are not constant. This is exponential. So we ought to be able to look at a data set, and if we have a common multiple, we're going to choose an exponential model. So on page 462, they walk us through the same process. These are our x values, these are our y values, but this is exponential. It's a multiplier. And so when we perform an exponential regression, which is one of your choices under your regression models, it gives us A, it gives us B. Look at R squared, 0.996. What does that tell us about the model? That is very close to 1, which tells us that this equation here, this equation that we get when we plug in this data, is an excellent model for the data we were given. So in this case, we definitely would use this to find approximations. Okay, let's keep moving. 463. Now, if we look at this graph, this data is going to, if we look at the graph, put it in and look at the graph, it looks like a log function. So they did a linear regression, not a linear, a natural log regression. And here's our data. So look at this, A plus B ln of x. They give us A, they give us B. So we plug those in, and this is the model for this data. So if you enter this data, it might be a good idea to go ahead and look at that scatter plot like we just did. If the scatter plot looks like a log curve, then you're going to use the natural log regression. Okay. So just a reminder of some of the others. We've talked about linear. We talked about polynomial functions, so we talked about linear and quadratic. We've talked about exponential. It's your multiplier. We also looked at square root. And now with square root, we're going to have a constant second difference. But this time, it's going to be between the x values because that's what I'm taking the square root of. Okay. So if we look at this, if we look at the constant differences in our x values on page 469, this is talking about the age of a tree given its diameter. And if we look at this, the second difference is constant. If we graphed it, this graphing is actually my favorite way. Graphing it and looking at the graph, this looks like a square root function. So that would lead us to using a square root model. Okay. So on page 470, they give us another example here. And here we have it increasing. The first differences are not constant. The second differences are not constant. We look at the ratios. They're close. So we're going to do an exponential regression. Exponential regression. It looks like an exponential curve. It actually almost looks like a line, which is probably why they tested the first differences. And I guess you could say it looks like the right half of a parabola, which is why they tested the second differences. But when those two failed, they looked at the ratios. And when you do the exponential regression, what they have done is they have drawn the model through the data. And look how close that equation models the data. Almost goes through all the data points. And if we look at our R squared, how close is that to 1? That's an excellent model. Okay, and so let's say you have some data and you enter it and you can't really tell. And so you try a couple of different things. Could it be quadratic? Could it be cubic? Could it be exponential? And so if we look at all of these and we take a look at R squared, R squared, R squared, of these, if you had to pick a model, I would go with the cubic because our R squared is closer to 1 with a cubic regression model than with the others. Okay, so you have a few problems to practice today. I want you to work together. I want you to have fun with this. Enter it on your calculator. Talk about which one you picked and why, and we'll go over these on Monday.